Our time-of-flight secondary ion mass spectrometer, Tof Sims, is an instrument for chemical or elemental analysis of solid samples. The simplest way to describe SIMS is to picture an electron microscope. Instead of a simple image, the pixel data of SIMS consists of mass spectrums where every pixel holds the data of the chemical representation of the sample. Time-of-flight secondary ion mass spectrometry is a surface-sensitive analytical method that uses pulsed ion beam to remove molecules from the very outermost surface of the sample. The particles are removed from the atomic monolayers on the surface. These particles are then accelerated into an electrostatic analyzer with 3 electrostatic sectors, and their mass is determined by measuring the exact time at which they reach the detector, hence the definition, time of flight. This is how our Tof Sims is built to work. Tof Sims data is collected by bombarding a sample with a pulse of primary ions, which in turn spud as part of the sample, generating secondary ions, which are pulled to the analyzer by an electric field. The secondary ion flight path has 3 electrostatic sectors which bend the ion trajectory, creating a long enough flight path to separate masses of the ions by flight time. Lighter ions arrive at the detector faster than heavier ions. It is very important that the material which is going to be analysed is brought into the laboratory the proper way, because Tof Sims is sensitive to the outermost 1 or 2 molecular layers. To avoid improper results, the material needs to be held in a container that contains no other residue other than the material itself. Even volatile substances can cause sample contamination. The main fields of research where Tof Sims has proven useful are energy devices like fuel cells, batteries, supercapacitors, catalysts, geological samples, metals, glass, polymers, pharmaceuticals, and biomaterials. In our research in energy devices, we often need to answer questions as to why the performance degrades. Tof Sims has proven to be an irreplaceable tool determining what has gone wrong when a device has failed or is showing poor performance. Element mobility and segregation within cells has proven to be one of the major influences in performance degradation for solid oxide fuel cells. Tof Sims can precisely pinpoint the regions where element segregations have occurred, and by these processes, reduction of performance or complete failure has occurred. Solid oxide fuel cells are based on oxide ion conductive materials, which gives another approach on failure diagnosis. With the help of Tof Sims high mass resolution, which can separate oxygen-18 isotope from H20, the use of isotope marking with O18 can contrast regions of low performance in fuel cells. Our Tof Sims may not be the best tool for quantification of different isotopes on geological samples, but it is one of the best instruments available for isotope distribution studies. Most methods for quantification are limited, with large analysis areas. For example, laser ablation ICP-MS has a minimum usable analysis spot of at least 100 microns, where Tof Sims has a usable spot size of less than 100 nanometers, which is 1,000 times smaller. The smaller spot size allows to closely analyze isotopic changes in small crystallites with the size of 1 micron or less. Geological samples were formed during a long period, and the small size allows to interpret the way the crystallites were formed and which elements were dominantly present in what time frame. The continuous development of sputter performance has opened new fields for time-of-flight dual-beam depth profiling. Tof Sims features combined with mass makes Tof Sims dual-beam depth profiling best suited for the analysis of unknowns. This means there is an option to carry out failure analysis, interface analysis, and reverse engineering. The main interest with glass samples are mostly regarding the uniformity and elemental composition of different coatings. Nowadays, most glass products have some kind of coating layer, like anti-reflective or anti-fingerprint coatings on cell phone displays, or even heat-reflecting coatings on window glasses. The dielectric properties of glass create a lot of difficulties in the analysis of these types of samples. However, our instrument is equipped with electron and argon ion flood guns, which give excellent charge reduction capabilities, allowing us to do depth profiling analysis on most samples. The dielectric properties of glass create a lot of difficulties in the analysis of these types of samples. However, our instrument is equipped with electron and argon ion flood guns, which gives excellent reduction capabilities, allowing us to do depth profiling analysis on most samples. Static Sims with large primary ions like C60 fullerene is an ideal analytical technique because it detects both large, complex molecular ions and fragment ions with ultimate sensitivity to provide detailed structural information. A liquid metal ion gun with gallium source does not allow to study polymers or even distinguish polymers from organic contamination. With C60 fullerene primary ions, the secondary ions are more molecular fragments, which, for example, allow the study of polymerization reactions that occur on catalyst materials. When we are dealing with metal samples, the variety of questions are large. Most metal samples are alloys where different crystalline regions need to be analyzed, or the topmost layer of an alloy needs to be determined. Also, impurity studies are common, where oxide or hydride distributions are analyzed throughout the material. Our Tof Sims has also been used for process control analysis by depth profiling and cross-section imaging of electrochemical deposition of different layers on metals. Coatings are of increased importance for many industrial products for reasons of decoration as well as stability. There is a technological challenge caused by various substrates used because different classes of material are applied as coatings and because many products are reshaped after the coating step. Crater formation and adhesion problems are therefore among the most common analysis requests. Analysis done by Tof Sims is able to determine the composition, structure, orientation, and spatial distribution of molecules and chemical structures on the surface of various biomaterials. This technique can be used to determine the distribution of the different ingredients, including the drug itself, within the tablet. The detection and quantification of trace metals is an important analytical task in the semiconductor industry. Tof Sims can detect all elements with mass resolution up to 11,000, which separates organic molecules from a lot of isotopes with the same weight. The analysis of different inks on paper can be of great value, especially if it is necessary to determine which signature on an important document was applied first, or whether parts of a document have been changed after the document was signed. Diffusion through polycrystalline metal oxide. One major advantage of Tof Sims is the opportunity to combine high lateral and high depth resolution. In the so-called dual beam depth profiling, it is possible to optimize the analysis beam and the sputter beam independently and measure 3D chemical profiles. The operator can choose between highest lateral resolution, called unbunched mode, and high mass resolution mode, called bunch mode, when doing analysis. In unbunched mode, the lateral resolution can be less than 70 nanometers. However, the mass resolution in this mode is about 600 nanometers, which is considered only unit resolution. With unbunched mode, the mass spectrum consists of wide square-shaped peaks, giving mass unit separation of ion with no possibility to separate aluminium hydride from the silicon peak. Bunched mode, as the name implies, is a method where the pulse of primary ions is slightly decelerated, creating a bunched pulse of ions. Because bunched pulse has much shorter interaction time, the mass resolution is increased by orders of magnitude. With bunched mode, lateral resolution of a few hundred nanometers with mass resolution up to 11,000 can be achieved, reducing the problem of interfering peaks. The focused ion beam has become a powerful tool for site-specific 3D imaging of submicron features in a sample. In this FIB tomography technique, the sample is sequentially milled using an ion beam perpendicular to the specimen, while imaging the newly exposed surface using an electron beam. This so-called slice and view approach allows larger-scale nanostructures to be characterized across the many imaging modes available to an SEM, including secondary electron, backscattered electron, and energy-dispersive X-ray measurement. The process is destructive since the specimen is being sequentially milled away after each image is collected. The collected series of images is then reconstructed to a 3D volume by registering the image stack and removing artifacts. The predominant artifact that degrades FIB tomography is iron mill curtaining, where mill patterns form large aperiodic stripes in each image. The iron mill curtaining can be removed using destriping algorithms. Our time-of-flight secondary ion mass spectrometer, Tof Sims, is an instrument for chemical or elemental analysis of solid samples.